Climbing robots, such as the Lemur 3 robot pictured here, have great potential to support planetary exploration. They can allow scientists to gather data from steep or vertical sites that would be inaccessible to wheeled rovers. The dominant approach to ascending rocky cliff surfaces is the use of microspine grippers. A microspine is a sharp hook that can catch on small asperities in the rock. Grippers contain multiple microspines in parallel, with flexures allowing motion between them. A typical microspine design is shown here, adapted from a perching gripper mechanism. The three flexures provide axial compliance for load sharing and normal compliance to conform to the surface, while preventing spine rotation. Microspines were originally fabricated through Shape Deposition Manufacturing, or SDM, where alternating CNC milling and urethane casting steps can form a part with both rigid and flexible elements. Later, metallic microspines were developed to survive in space environments. These use long serpentine flexures to provide compliance despite the higher material stiffness. More recently, microspine-tipped acrylic leg slices were added to a Rex robot. The length of the slices ensures sufficient compliance despite acrylic's higher stiffness. This would not be applicable in the smaller form factor. In this work, we instead propose the use of additive manufacturing for microspine fabrication, specifically Fused Deposition FDM, as a faster and less labor-intensive alternative to prior techniques. We present a hybrid additive and casting approach, as well as a fully additive approach to microspine design. We also provide a model of microspine stiffness to help designers convert designs between different approaches. And we experimentally verify the mechanical characteristics of the new microspines to ensure there will be no reduction in performance. In the hybrid process, rigid elements of the microspine are 3D printed with the addition of breakaway mold walls. The flexures are cast out of urethane, as in the SDM process, and the walls are then removed to leave the finished spine. This eliminates the need for CNC machining steps, but reduces the maximum load the spine can support due to poor adhesion between the materials. In the fully additive FDM process, more significant design changes are required. For ease of printing, we use only a single material, a flexible TPU, with a stiffness in between that of the rigid and flexible urethane resins. This significantly increases the stiffness of the flexures, so a serpentine flexure geometry is applied to lower the stiffness back down. However, the serpentine flexures are unable to prevent rotation of the spine, so the supporting tendon is instead converted into a parallel flexure, which constrains the spine angle. Without rigid elements, the microspine requires additional reinforcement to prevent out-of-plane twisting. This is provided by extending the length of the hook shaft. Finally, the softer material is unable to adequately constrain the hook, so additional material is added around the hook for support. The serpentine flexure geometry must be carefully determined to compensate for the change in material stiffness. To this end, we develop a linear elastic model for microspine stiffness. The supporting tendon stiffness contribution can be found by superposition of the axial and bending loads and projection onto the axial displacement vector. The serpentine flexure model is directly taken from prior literature, and the contributions of the three tendons can be combined to get the normal and axial stiffness predictions. We validate this model through tensile testing of three different serpentine tendon geometries, as well as the original SDM geometry. Though the linear model only holds for small displacements, the relative ordering is maintained, and thus the model can be used to make stiffness comparisons even between designs with dramatically different material properties. Further tensile testing results confirm close agreement between our tuned FDM design and the reference SDM design for both axial and normal stiffness. Additionally, cyclic load testing reveals that degradation of the FDM microspines due to fatigue occurs at a slower rate. Finally, FDM spines can support larger loads before material failure, as there are no material interfaces that can delaminate. In conclusion, we have developed a novel FDM microspine design which can be manufactured significantly faster for small batches, enabling rapid prototyping cycles. These spines require less labor and equipment to produce. Their maximum load is higher, so they require less frequent replacement due to overloading. Their stiffness and fatigue resistance are also comparable or superior to FDM spines. One disadvantage is that the dimensional tolerances of the spine are limited by the 3D printer precision, but this is not a concern for most applications. Future work in this area could investigate the sensitivity of FDM spines to thermal extremes and UV degradation. There's room for further innovation on the design of the flexure geometry. New materials could solve the adhesion issues of hybrid microspines, and the single material FDM design could be adapted to different manufacturing methods for easier mass production. Lastly, these microspines can be used in the development of new climbing robots. For instance, our current climbing robot under development, shown here, uses FDM microspines for all of its grippers. Thank you for listening.